Assalamu alaikum dear students. I welcome you to the 8th lecture of probability and stochastic processes. In previous 7 lectures, we thoroughly covered the problems involving finite sample spaces. That is, those problems which have a finite number of total possible outcomes. We covered many topics, particularly we covered the concepts of conditional probability, joint probability, total probability, and Bayes rule. We also covered a few simple but interesting examples of Bayes rule. We started talking about those random phenomena which have infinite sample spaces. That is, the possible total number of outcomes is infinite. We talked about a few simple problems with infinite sample spaces. For example, we talked about the random orientation of a circular disk as it is thrown on a floor which has been marked with x and y axes. So as the disk comes to a rest, its orientation is a random phenomena, and this can be of any value between 0 and 360 degrees, and it can attain all possible real numbers between 0 and 360 degrees if you are measuring the orientation in degrees. And this disk can give you an angle of any number between 0 and 2 pi if you are measuring the angle in radians. We also talked about random placement of a foot of a person who is walking on a partitioned footpath. And then we extended this idea to find the random location of a circular disk as it is thrown on a floor which has been marked with either only horizontal lines or horizontal and vertical lines. These were simple problems. Today, we'll talk about more complex problems with infinite sample spaces. In the last lecture, we started talking about trains coming at a downtown subway station and the random nature of the waiting times that are experienced by the commuters. Today, we will continue the discussion of random arrival times of commuters on a subway station. So let's have a look at this problem which is shown in this slide. The first thing that you should remember about this problem is that this is a real life problem and it has many unpredictable random parameters that are going to affect the thing that we are going to observe. But we can only work with a simplified model of the problem. If you look at a real world situation where trains do come and leave from a railway station, then there is everything that is unpredictable. The arrival time of the train, the departure time of the train, the amount of time the train spends on a particular station. All these things are affected by many unpredictable events. For example, if a commuter enters a station, it's not possible for him to predict if the train is standing there and waiting for him to come on board, or if he is going to wait for some time before the train arrives. The arrival time of the next train is highly unpredictable phenomena because it depends on so many unpredictable things that have happened to the train. For example, what was the time the train started its first run early in the morning? What kind of crowd it carried throughout the day till the time we are going to observe it? How much time it spent on each station? How many commuters it had to pick up from all the stations it visited? How many commuters had to get down? All these things are going to affect the arrival time of the next train. Similarly, the inter-arrival time, that is, the arrival time of the next train once the current train departs, is also unpredictable. But we can make this inter-arrival time a predictable and fixed quantity because due to the available large number of trains and the effort the scheduling staff puts in to make their train system predictable and usable, we can assume that they are going to have trains coming after each other at a certain amount of time. So we can assume that, for example, the eastbound train is going to come 10 minutes after the current train departs. Similarly, the amount of time that a train spends on each station is highly unpredictable and random. In reality, it depends upon the number of commuters that have to get off the train and number of commuters that have to get on the train. In reality, the train departs as soon as all the people who wanted to get off the train have stepped down and all the people who wanted to ride the train have stepped in. But in an effort to simplify our real-life unpredictable phenomena, we are going to assume that the amount of time the train spends on the downtown subway station is fixed. So that's why we have assumed that eastbound train comes every 13 minutes, stops for 3 minutes and then departs. And once the current train departs, exactly 10 minutes after that, the next train comes, stops for 3 minutes and departs. So these aspects of the problems have been assumed to be fixed and predictable. The thing that we have assumed to be unpredictable and random is the arrival time of a certain passenger. We cannot predict when the next passenger is going to come, but once he enters, he can find many things happening on the platform. In reality, he may find that the train is actually standing there waiting for him to get on board, which will make him very happy. Another scenario is that he may find that the train is just approaching the station and is going to stop in few seconds. That will also make him very happy because he did not have to wait for long and he will board the train as soon as it comes to stop. A third possible scenario is that there is no train. Then the commuter will go on the platform and start waiting and continue to wonder how many minutes he has to spend waiting for the next train. And a fourth scenario is that as soon as he enters the station, he sees his desired train departing, which will make him a little bit angry because now he has to wait a maximum amount of time for the next train to arrive. But we will ignore all these variables to have a simplified model. We will assume that the commuter suddenly and magically appears at the platform. We will ignore the time it takes for the commuter to enter the station, walk down the stairs, and actually reach the platform. So we will assume that at a certain instant of time, the commuter appears in front of the train. And if the train is standing there waiting for him to get on board, he will get on board instantly in a trillionth of a nanosecond. We will assume all these variable quantities to be not present to have a simplified model. So scenario is like this, that a commuter appears suddenly on the platform. If the train is standing there, he will get on board instantly, and once the stoppage time of the train has passed, that is 3 minutes for the eastbound train that we have assumed, the train will suddenly vanish. It will not slowly move out of the station, it will suddenly vanish, ending its stoppage time. So there are only two things that the commuter will observe when he enters the station. Either the train is there, standing, waiting for him to get on board, or there is no train. With this simplified model, let's look at the next slide, which presents this model for single train, the eastbound train, and what are the things that a commuter will observe once he enters the station at a random time. In this slide, you see that our sample space is one-dimensional. And in this one-dimensional sample space, you see color bands of red and green. The red represents those instances of time when there is no train. The commuter has to wait for the next train. and the green band represents those times when the train is there for the commuter to ride. As you can predict, you can expect, this is a repetitive phenomena. Once the waiting time is over, the train appears, it is there for 3 minutes for the commuters to get on board, and then it leaves and the waiting time starts again. So we do not have to consider the sample space which spans the whole day. We can restrict our attention to just a 13-minute interval. In this 13-minute interval, 3 minutes represent those instances of time when train is there, and 10 minutes are those instances of time when there is no train. And the commuter enters at random amount of time and he finds him either having to wait for the train or getting on train which is waiting for him. It is quite easy to find probabilities of different events in this one-dimensional sample space. As I said, we have to restrict our attention to any contiguous 13-minute interval in the whole day, and furthermore, we have to assume that the commuter enters the station at a time which is equally probable to occur at any instance in this 13 minutes. So, the probability of a person not having to wait for the next train is 3/13, because the probability of something happening in a given interval is proportional to the length of the interval, and the length of the interval representing those instances of time when he does not have to wait for the train is 3 minutes, and the total length of the sample space is 13 minutes. So probability of that person not having to wait for the next train is 3/13. Similarly, the probability of that person having to wait 2 minutes or less, either he will wait for 0 minutes, that is he will find the train there, or he will wait at most 2 minutes. 1.5 minutes is fine, 1 minute is fine, 30 seconds is fine. The probability of this event is the length of those instances of time where the person has to wait for the next train for at most 2 minutes or 0 minute, that is 5 minutes. 3 minutes represents those instances of time when he does not have to wait, and 2 minutes represents those instances of time when his waiting time is less than 2 minutes. So probability of that person having to wait for the next train for less than 2 minutes is 5 divided by 13. You can also find probabilities of more complicated events, particularly conditional probabilities. For example, the probability of that person having to wait for at most 2 minutes, given that he does have to wait, is 2/10 or 1/5. Because this given information, the conditional event is that he does have to wait. When he arrived at the station, he did not see a train waiting for him, so he had to wait. With this additional information, the sample space has been reduced to 10 minutes. And out of these 10 minutes, now the probability of him having to wait less than 2 minutes is 2 minutes. So 2 divided by this conditional event is 2/10. You can find probabilities of other interesting events for this type of situation, but this problem becomes more interesting when you consider two trains. That is, you consider that you are watching this phenomena at the central station where north-south and east-west lines meet. In last lecture, we have been saying east-west line and north-south line, but we have to be more precise. We should pick one direction on the north-south line and one direction on the east-west line. Let's suppose these two trains run on their respective routes according to their own schedule. That is, the eastbound train arrives every 13 minutes, stops for 3 minutes and then leaves. And the southbound train comes every 12 minutes, stops for 2 minutes and then leaves. This joint random phenomenon can be observed from the viewpoint of two commuters. One wants to ride the eastbound train and the other wants to ride the southbound train. So these two commuters enter the station at two instances of time, and these instances of time are independent of each other and random. Since these two trains run periodically, the southbound train every 12 minutes and the eastbound train every 13 minutes, we can expect one of the four things to happen when the two commuters enter and observe what is the status of their respective trains. The first scenario is that they will see both of the trains standing at two platforms and they will ride those trains and go their way. The second scenario is that only the eastbound train will be there standing and the southbound platform will be empty. And the third scenario is that the southbound train will be there but the eastbound platform will be empty. And the fourth scenario is that there will be no train and both of the commuters have to wait for some time before their trains arrive. This joint observation of eastbound and southbound train can be modeled as a two-dimensional infinite sample space. And since the periodic phenomena is there, we have to restrict our attention to 13 minutes of the observation time on the eastbound train and 12 minutes of observation time on the southbound train. So the interesting area that we are going to analyze consists of a rectangle, 13 units along the east side and 12 units along the south side, where units represent minutes. On this slide, you see that the phenomena is random in two dimensions, but we only need to consider any rectangular region which is 13 units on the x-axis and 12 units on the y-axis, where x-axis represents the observations of that commuter who is going to travel to east, and the y-axis represents observations of that commuter who is going to travel towards the south. Once you restrict your attention to this 13 by 12 region of the whole sample space, which is 1 day long, you see that the total area is 156 units, that is 13 into 12. Furthermore, if you assume that probability of any event is proportional to the area of this two-dimensional space that is represented by the event, then it is very easy to find probabilities of different events. For example, what is the probability that none of the commuters, neither the eastbound nor the southbound, have to wait for their trains? That is, when they enter, both of them find their trains standing there for them to get on board. This is represented by that region which is green on the x-axis and green on the y-axis, which is 3 units by 2 units. So area of that region is 6. So the probability of none of the two commuters having to wait for their trains is 6 over 156. You can simplify this fraction to get a more meaningful answer. There are other events that you can work on. For example, what is the probability that none of the commuters have to wait for more than 3 minutes? That is, either they find their trains standing there or they wait for 2 minutes, 1 minute, 1.5 minutes, but not more than 3 minutes. This region is represented by that green region and 3 minutes to the left, and on the y-axis that green region and 3 minutes below. So the total region is 6 units by 5 units, or an area with total area of 30 units, 30 square units. So probability of none of the commuters having to wait for more than 3 minutes is 30 over 156. This slide also shows that the probability of eastbound person having to wait longer than the southbound person is 50 over 156. Why? When they have to wait and the eastbound person has to wait longer than the southbound person, then we assume that the y value is larger than x, and this is represented by an upper triangle of area 50. The upper triangle bisects the red region into two areas. One represents where the eastbound person has to wait longer than the southbound person, and the other triangle represents where the southbound person has to wait longer than the eastbound person. So probability of southbound person having to wait longer than eastbound person is 50 over 156. You can also work on conditional events. For example, what is the probability that the southbound person has to wait longer than the eastbound person given that they do have to wait? When I say they do have to wait, I mean none of them find their train standing there. So the reduced region of uncertainty is the red region, where both of them arrive and they find that their trains are not there. With this given information, the probability of southbound person having to wait longer than the eastbound person is just the area of that upper triangle divided by the area of new reduced region of uncertainty, which is 100 square units. The probability of southbound person having to wait longer than the eastbound person, given that both of them have to wait for their trains, is 50%, 50 over 100. If you feel that the inclusion of green bands, that is the time when trains stop at the station, makes this problem slightly more complicated, you can have a simpler version of the problem. And this problem can be considered as a situation on a local bus stop. Suppose there is a bus stop, and on that bus stop, two people, one boy and one girl, ride a certain bus every day. So assume that the bus comes every day at a fixed time of 8:10, 8 o'clock, 10 minutes after 8 o'clock. And the boy and the girl arrive at the bus stop any time between 8 and 8:10. So their arrival time is random, and every time between 8 o'clock in the morning and 8:10 is equally probable for their arrival. Furthermore, both of them arrive independently of each other. Here, we will assume a simplified model that they arrive at a random time between 8 and 8:10. Both of them arrive independently of each other, and once the clock strikes 8:10, a bus comes there magically, and suddenly they ride the bus instantly and bus vanishes. So this random phenomena is a joint observation of two arrival times. Both of them lie between 8 and 8:10. And the sample space is a two-dimensional area of the plane, where we can assume that along the x-axis we are observing the arrival time of the boy, and on the y-axis we are observing the arrival time of the girl. So this area is between 8 and 8:10 and 8 and 8:10. So it is 10 by 10 square with a total area of 100 square units. And the random observation is a number x comma y, where x represents the arrival time of the boy and y represents the arrival time of the girl. So observation is a point in this 10 by 10 region. So in this point, we can find many interesting events and find their applications. For example, let's consider this phenomena that the boy comes before the girl. Where in this 10 by 10 region this event is represented? It is represented by all those pairs of numbers x comma y, where x is small and y is large. X small means the boy arrives at, for example, 8:03 and the girl arrives at 8:04. So all those pairs of points where y is larger than x represents that event where the boy arrives before girl. And this is represented by the upper triangle. If you draw a line diagonally, then the upper triangle represents the event that the boy arrives before the girl. And probability of this event is 50%, 1 over 2. The next interesting event that we can consider is that what is the probability that they will see each other for at least 2 minutes. They arrive at the bus stop, bus arrives exactly at 8:10. So what is the probability that they will be able to see each other for at least 2 minutes? This is going to happen if both of them arrive at 8:08 or before that. So collection of all those pairs of numbers x comma y, where x and y both lie between 8 and 808, is represented by a smaller square of area 64. So probability of them seeing each other for at least 2 minutes is 64%. The third event can be this, that what is the probability of boy being able to see the girl for at least 2 minutes, given that he arrives before the girl. If you look at slide, you will see that probability of this is also 64%. This slide shows that the conditioning event is that boy arrives before girl, and that is the upper triangle. In this slide, you will see that on the lower left corner of the slide, a triangular region has been marked with vertical lines. That is the conditioning event, that is the boy arrives before girl. And the blue smaller triangle represents that once he has arrived before girl, he is able to see her for at least 2 minutes. And the ratio of these two triangles is still 64%. And the last event that we are interested in is that what is the probability that the boy is able to see the girl for at least 2 minutes if he arrives after her. And that is shown in this slide as the lower right region, where the lower bigger triangle is the conditioning event, that is the girl arrives before boy, and the smaller blue triangle represents the event that they are able to see each other for at least 2 minutes. And the ratio of these two triangular regions is again 64%. So what's the moral of the story? It is that the event of them being able to see each other for at least 2 minutes does not depend who arrives first. And this makes sense because when boy sees the girl is able to see him, and changing the role of boy and girl does not alter the probability. The probability of them being able to see each other for at least 2 minutes is 64%, and it does not depend on whether boy arrives at the bus stop before the girl or the girl arrives at the bus stop before the boy. So far we have been talking about simplified versions of real life phenomena. Let's look at another interesting example which is academic in nature. Let's take a unit interval, a segment of real line between 0 and 1, and then pick two numbers between 0 and 1 randomly. These two numbers do not depend on each other, and every number between 0 and 1 is equally likely to be picked. Once you have picked the two numbers, then most probably the line interval between 0 and 1 gets cut into three segments. The first segment is between 0 and the first number. The second segment is between the first number and the second number, and the third segment is between second number and 1. It is quite possible that the two picked numbers are the same, but probability of that happening is very small because this represents an isolated point in the two-dimensional sample space. Similarly, it's possible that the two picked numbers fall on either 0 or 1, but probability of that happening is also 0. The only feasible events in this case are those regions of sample space which have non-zero area. And the sample space is a two-dimensional 1 by 1 square, where the x-axis represents the first number and the y-axis represents the second number. There are many interesting events that could be investigated for this sample space, and next slide shows such an event. In this slide, we are interested in finding the probability of this event that the leftmost segment of unit interval is the smallest. That is, we pick 2 points and the interval between 0 and the first point closest to 0 is the smallest and the remaining two segments are larger than this smallest segment. Let's be clear about one thing that is applicable to the discussions about this partition of unit interval. It's quite possible that we reverse the roles of x and y, where x is the first number and y is the second number. And we can work with either upper triangular region or lower triangular region, and everything is symmetric across this diagonal line. But for the sake of completion, we will consider x and y two distinct numbers, and we will consider this as two separate cases when x is to the left of y and when y is to the left of x. Coming back to the slide, we are interested in this event that the leftmost segment of the unit interval is the smallest. Now suppose x is smaller than y, that is, x is closer to 0 and y is closer to 1. If that's the case, then we are only interested in the upper triangular region of the sample space, because we have assumed that x is smaller, y is larger, and this is only true for the upper triangular region. The next constraint would be that x must lie between 0 and 1 by 3, because if x lies beyond 1 by 3, then this segment is larger than 1/3 of the unit interval and remaining length is less than 2 by 3. And if you are going to divide that 2 by 3 interval into 2, then one of those intervals will be smaller than this leftmost segment. So this constraint is that x must lie between 0 and 1 by 3. It can be 0.1, it can be 0.2, but it must lie between 0 and 1/3. This constraint has been graphically marked as a region with vertical lines. The next constraint is that y should be greater than 2 times x. Why is it so? You see, the leftmost segment is the length between 0 and x, and the middle segment is between x and y. If y is at least twice the value of x, then y is as far away from x as x is from 0. So distance from origin to x is x and y is 2x or more. So this interval between x and y is now larger, making sure that the leftmost interval is smallest. This constraint has been graphically represented with horizontally marked lines. And the third constraint is that 1 minus y should be greater than x. Why? Because if you look at this diagram, the distance between 0 and x represents the leftmost segment, and distance between y and 1, that is 1 minus y, represents the length of the third, the rightmost interval. If this interval is going to be larger than the first interval, then all the constraints are satisfied. So third constraint is that 1 minus y, the length of the rightmost interval, is also larger than the leftmost interval. And this constraint has been marked on this slide with the yellow triangular region. And if you combine all these constraints, you will get a region which is graphically marked as yellow triangle, that portion of the yellow triangle which has horizontal as well as vertical lines marked on it. And this region represents the probability of the 2 points x and y having values in such a way that the leftmost interval is the smallest and x is on the left. There is a corresponding triangular region for the case when y is on the left and x is on the right. And on this slide, you will see on the lower right region the two triangles for these two cases marked in blue. The total area of the two triangles happens to be 1/3. So probability of the leftmost interval, the leftmost segment of the unit interval being the smallest is 1/3. Let's look at another interesting event in this partition of unit interval. What is the probability that the leftmost segment is largest of the three segments? This is graphically represented in next slide, and again we are going to work with that case where x is on the left of y, that is the number y is larger than x. So our region is upper triangular region. And the next constraint is that x must be between 1/3 and 1. The reason is that now x being on the left is representing the distance between 0 and x, which is the leftmost interval. And we want this interval to be the largest. If this point happens to fall between 0 and 1/3, then this cannot be the largest of the three, because the remaining length is larger than 2/3, and no matter which way you divide this length, which is larger than 2/3, in two segments, one of them is going to be larger than 1/3. Hence, the first constraint is that the left point x should be larger than 1/3, and it can lie on this interval between 1/3 and 1. This constraint is graphically represented by vertically marked lines. The next constraint is that the second point y should be less than 2 times x. Why is it so? Because the first interval is represented by the length between 0 and x. And if this is going to be the largest, then this interval x to y should be smaller than this. So 0 to y should be smaller than 2 times 0 to x. If this is satisfied, then the middle interval should be smaller than the leftmost interval. And this constraint has been graphically represented with horizontally marked lines. The third constraint is that 1 minus y should be less than x. Why is it so? Because 1 minus x represents the rightmost interval of the unit line. And if this is going to be smaller than x, then 1 minus y, this length should be smaller than 0 to x length. If we combine all these constraints, you will see in this slide that the region which satisfies all these constraints is a four-sided irregular polygon which is touching the diagonal line, and this is that portion of the yellow triangle which has both horizontal and vertical lines. And area of this is 1/6. But there is a corresponding four-sided polygon for that case where y happens to be on the left side and x happens to be on the right side. That is, y is smaller than x. And then we will work with lower triangular region, and that four-sided polygon will be symmetrically mapped. Symmetrically means symmetry across the diagonal line. That polygon will be symmetrically mapped to the lower region, and the total region representing the event that the leftmost interval is largest is a five-sided irregular polygon, and the total area of this polygon is 1/3. So once again, the probability of leftmost interval being the largest is 1/3. Before we end today's lecture, let's have a look at a couple of events on this random partition of unit interval. The two cases that I'm going to consider next are more complicated than previously considered cases, but they are also very interesting. The next event I'm interested in is that what is the probability that the longest interval is longer than 0.75. Please note that the longest interval could be the first one, the middle one, or the rightmost one. I'm only interested in wherever the longest interval is, what is the probability that it is between 0.75 and 1. That is, it is longer than 0.75. This is graphically shown on the next slide. And in this slide, we see that the first case when the longest interval is going to be longer than 0.75 is the case when the longest interval is the leftmost, between 0 and the point which is closer to 0. This is going to happen when the next point is away from 0.75. That is, both points x and y lie between 0.75 and 1. When both of these points x and y lie between 0.75 and 1, and it does not matter which of the 2 points is closer to 0 and which of the 2 points is closer to 1, as long as both of them lie away from 0 by a distance larger than 0.75, the longest interval, that is the leftmost interval, will be longer than 0.75. And probability of that happening is that both x and y lie between 0.75 and 1, and this region is represented by a blue square near the top right corner of the sample space. And probability of this happening is 1 over 16. Then the second case when the longest interval could be longer than 0.75 is the case when this interval is the rightmost. And this is going to happen if both of the points x and y lie between 0 and 0.25. And it does not matter which point is on the left, which point is on the right. As long as both x and y lie between 0 and 0.25, the rightmost interval will be bigger than 0.75. So probability of this happening is 1 over 16, and this is represented in this slide by a blue square near the origin. Now the most interesting case is when the longest interval is middle one. If that's the case, and we assume that x is on the left and y is on the right, then x can lie anywhere between 0 and 0.25. It cannot lie beyond 0.25 because then the remaining length will be less than 0.75 and the longest interval could not be more than 0.75. So x is on the left and x lies between 0 and 0.25. Then wherever x lies, the y has to lie beyond the value of x plus 0.75. So if x lies at 0.1, y must lie at 0.85 or beyond. And if x lies at 0.2, the y must lie between 0.95 and 1. So whatever the value of x, y must assume a value which is larger than x plus 0.75. When you combine these constraints, you get a triangular region which is shown on this slide near the top left corner. There is a corresponding region, triangular region, symmetrically placed across the diagonal, and this represents when y is on the left. When y is on the left, then y has to lie between 0 and 0.25 and x must lie beyond y plus 0.75. Combine these constraints and you'll get a triangular region which is shown on this slide in blue color at the bottom right corner of the sample space. If you combine all these blue areas, the probability of longest interval being longer than 0.75 comes out to be 3 over 16. The last case that we are going to consider today is the event that what is the probability that the shortest segment is smaller than 0.25. Again, the shortest segment could be the leftmost, the middle one, or the rightmost. And we are going to consider these three cases separate. Suppose the shortest segment of the unit interval is the leftmost. And furthermore, suppose x is on the left and y is on the right. In this case, x must lie between 0 and 0.25 because we are asking for the leftmost interval to be the shortest, and this is between 0 and x. So x must lie between 0 and 0.25. When that is satisfied, then there are other constraints that point y must satisfy. When x lies between 0 and 0.25, there is some remaining length, and point y should fall on this length in such a way that both of these intervals are larger than the interval between 0 and x. If you combine all these constraints, that is, x lies between 0 and 0.25, and this interval is shortest, that is, 0 to x is shorter of x to y, and it is also shorter of y to 1. That is, y minus x is larger than x, and 1 minus y is larger than x. If you combine all these constraints, then you will get a region on the sample space which is shown on this slide in blue color. This four-sided polygon touching the vertical axis represents the case when x is to the left of y and the shortest interval is between 0 and x, and this is less than 0.25. There is a corresponding case when y is on the left. Then the region which represents this shortest interval being less than 0.25 is touching the horizontal axis, the x-axis, and this is shown on this slide in yellow color. Then the second case, that is shortest interval is on the right side of the unit interval. If that's the case, then there are two scenarios, one where x is on the left and the other where x is on the right. Consider the case where x is on the left. If x is on the left and the rightmost interval is the shortest and it is less than 0.25, then y must lie between 0.75 and 1. Not only that, x should fall in such a way on the remaining portion of the line that 0 to x should be larger than this and x to y should also be larger than this. That is, this interval is 1 minus y and x is larger than 1 minus y and y minus x is larger than 1 minus y. If you combine all these constraints, then the region is marked on this slide with dark green four-sided polygon touching the top of the sample space. There is a corresponding case where x is on the right, y is on the left, and the region between x and 1 is the shortest and it is shorter than 0.25. And you combine all the constraints and you get your region, which is marked on this slide with magenta, which is touching the right edge of the sample space. The most interesting case is when the shortest region is the central one. And if you assume your x to be on the left and your point y to be on the right, then y minus x represents this length, and this length must be smaller than 0.25. Not only that, but also y minus x should be larger than 0 to x, and it should be larger than y to 1. So y minus x should be between 0 and 0.25, y minus x should be smaller than 1 minus y, and y minus x should be smaller than x minus 0 or x. If you combine all these constraints, you get a beautiful four-sided, very narrow region on the sample space which is touching the diagonal line. This elongated region is shown in dark red. There is a corresponding region below the diagonal which represents those cases where x is on the right, y is on the left, and the middle portion represented by x minus y is the shortest and it is shorter than 0.25. If you combine all these regions, which represents that the shortest region, whether it is the leftmost, the middle one, or the rightmost, is shorter than 0.25, you find out that probability of this happening is 15 over 16. So this happens with a high probability. There are other interesting events whose probabilities you can find out, and you can formulate many events either absolutely or in a conditional probability sense and find probabilities of those events. For example, what is the probability that the shortest interval is shorter than 0.25 given that the longest interval is greater than 0.5, and so on and so forth. Some of these events have been solved in your class handouts, and some of these events are given as homework exercises, and I hope you will enjoy solving all these problems. To summarize what we have covered today, we have extended our discussion of those random phenomena where possible outcomes are infinite. We talked about arrival times of commuters, and we talked about random partitioning of unit interval. Some of the problems were real life, but we worked with a simplified model, and some of the problems are academic, but quite interesting and quite challenging. One thing you should remember, that so far we have assumed that all outcomes are equally likely. This is not the case in real life. And starting from next lecture, we are going to expand our discussion to those cases where some outcomes are more likely than the other. Till then, I wish you the best. Khuda Hafiz.